So the idea here is that if I have, to say it again, I have a vector space that's a span of 3 vectors, but one of them is linearly independent, V3 is equal to V1 plus V2, then I can use that dependence to remove V3 from the span and write the span as just the span of 2 vectors. And I was trying to argue that this extra freedom to choose the coefficients in different ways doesn't really change the span. So you've reduced the span by 1 vector, so the dimension is not 3, it's 2, and you can write the basis as either V1, V2, or V2, V1. So that goes to this other problem of given sort of this kind of vector, if you have this extra situation with a dependent vector. And we can do some examples like that maybe next week. Okay, so I think that is more or less what what we wanted to deal with for this one. So here, what I want. So now, I was more to sort of say about it in practice. But if you look at this section of vector spaces and linear systems, we have a new concept. We have the idea. Let's take a matrix that is in say row echelon form. Right, so it's a 3x4 matrix, and you can see this is an echelon form, right? And now it has here. Maybe I should write this so it's not. Okay, so this one has the variables are x, y, z, and w. Right, there's 4 variables, 3 equations underneath this matrix. This is the coefficient matrix. Think of this as the coefficient matrix of some linear system. Okay, well, now, if it's an echelon form, right? So it turns out, because it's an echelon form, I can consider the space row space. Okay? So row space of this matrix is a row space of the matrix, right? And basically, it's just the linear combination of all the rows. So it doesn't have to be an echelon form. So let's say that I started with just one that wasn't, with 1, 2, 3, 4, 5, 6. So row space would be the space A times 1, 2. These are now row vectors, plus B times 3, 4, plus C times 5, 6. Such that A, B, and C are members of R. Okay, this is row space. Now you can see here that it's going to turn out that I'm going to be able to, these vectors are not going to be linearly independent. Because what's going to happen, and we can check that. But the point is that, and in general, the row space, if I just write down the rows of a matrix, those row vectors are not going to be linearly independent, right? Not linearly independent. Now here, and this will go back to this problem here of, let's say I had a vector with some dependent vectors. How do I in a simple way find a basis? Okay. Well, here's a row space for the matrix, and the question is, are these linearly independent? Right. Well, we could check here and say, well, we'd set this to 0. A 1, 2 plus B 3, 4 plus C 5, 6 equals 0, 0, right? And then I could collect all these and see that I'm going to get the first component, A plus 3B plus 5C, A plus 3B plus 5C equals 0. And the second one, 2A plus 4B plus 6C equals 0. So although the column vectors are easier to see the equations because here they're all in one row, so they sort of, feel I'm sort of doing this, this, and this for the first equation, and this, and this for the second one. Now, so it has an augmented matrix, 1, 3, and if it's linearly independent, setting this to 0 will produce A equals B equals C equals 0. So I have 1, 2, 3, 2, 4, 6, 0, 0. And I can go, now here's something, let's think about this for a second. That I have two equations, but three variables. Well, in principle, I could use the second one to solve this for A and remove it from the first equation. Then I'd have one equation with two variables, B and C, and I could solve that for B in terms of C or C in terms of B, but I'm still going to have one variable. So there's no way I'm not going to have a free variable here. Okay? So these are not linearly independent. But if we go and do Gauss's method here, solve this system, let's see what Gauss's method does. Well, it's going to do, to get echelon form, -2 row 1 plus row 2 is going to give me 1, 3, 5, 0, and then -2, that is going to give me 0. And -6 plus 4 is -2, and -10 plus 6 is -4 and 0. Right, and then just to make it simpler, I could multiply row 2 by -1/2 row 2 to make the matrix look nicer. 0, 1, 2, 0. I get rid of the minus sign, I get rid of a factor of 2 here. Okay, well, this is an echelon form. Well, now here's the sort of, you can prove, and the proof is based on the idea that row operations just form linear combinations of the rows. So this row operation is going to produce this matrix by sort of adding combinations of rows to other rows. So they actually don't change the span. So here's the key result is, when I do Gauss's method, the span of these rows is the same as the span of these rows. So when I get to echelon form, though, let's see so these two vectors span the same space, right? What have I done? Oh, something is wrong with my mind today. No, I don't think so. It's okay. Yes. Okay. So yes. Okay. But the dissonance was thinking of I've got rows here, so instead of columns. So this all seems okay. However, let's see. Yeah, the problem here is, see, the coefficient matrix of these rows. The coefficient matrix is here 1, 3, 5, 2, 4, 6, right? So that's the matrix we're talking about. So the idea here is that but let's, and I think maybe because I'm using a row thing, it's like look at this coefficient matrix here for the system. See, I have 1, 2, I have 1, 2, I have 3, 4, I have 3, 4, I have 5, 6, I have 5, 6. What's happening is that each of these vectors here has become a column here, right? So let's see, in general, okay, this was an art. Okay, I chose here this is perhaps a subtle example, right? because I wanted this matrix, but that was the problem was that okay, so that's so this linear system of three, this space here is the, 1, 2, 3, 4, 5, 6. That is the row space of this matrix. But but then when I do the linear system here, so then I've gone to linear independence, and the problem that's why this example is subtle, because this is the correct, so everything's correct. This is the matrix, right? This is the row space of the matrix. This is the condition for linear independence. But then when I get the equations to solve this, it turns out it's this matrix, which you notice is this matrix looks like this, but the first row is the first column, the second row is the second column, and the third row is the third column. Now, the third row is the third column here. Now, it turns out that this relationship is interchanging rows and columns is an operation called the transpose. So if this matrix is M here, this one here is the transpose of the matrix. So curiously, in looking at this matrix, I ended up having to solve the matrix for the transpose. And so then so this matrix then has in it, I'm going to find the row operations of this one to come down here. And it turns out then that this transpose matrix also has a row space. And when I solve it, I come down here and find that this row space of one was originally spanned by 1, 2, 3, 2, 4, 6, is now spanned by 1, 3, 5, and 0, 1, 2. Well, these are linear independent, but if I solve this, I'm not going to, okay, that's beside the point here. I'm getting, the problem is so let's forget those comments for a second about this being the linear independence of rows here. I want to check the linear independence of these vectors. I want to solve this system, and I can see that A is leading and B is leading, but C is free, right? That means these are not linearly independent because I can find a solution. A plus B3 plus 5C equals 0. I can find a solution of this where A, B, and C are not 0. For example, I can choose, say, C here equals -1, so that B is going to equal 2 because C is -1. So B is 2. And this would be A plus 2 3s is 6 plus -5 equals 0. And that's 6 plus -5 is 1. So A has to equal -1. So I found a solution with A -1, B equals 2, and C equals -1. That will mean that these three vectors do not imply that A equals B equals C equals 0, so that these three vectors are not linearly independent.
How do we find out that C equals -1?
Excuse me?
How do we find out that C equals -1?
I chose it because it's free.
Okay.
If you have a free variable, you can choose it because free.
Okay.
That's the point. If it wasn't free, you couldn't choose it. So if it wasn't free, it might be forced to be 0.
Mm-hmm.
Okay, so then this set of 5, 6 is not linearly independent, okay? So that shows that these rows are not linearly independent. Then the question is, let me see, 3, 4, 5, 6. Well, how would I find a linearly independent set of these vectors? Well, and the way to do it, I jumped the gun up here and talking about this is that Gauss's method works by making a basis for row space. Okay, so here let's apply it to this one here. Let's apply directly we can do -3 row 1 plus row 2 and -5 row 1 plus row 3. So this matrix here, you have 1, 2. Oh no, I don't. Yeah, I need I get 0 there, but I have -3 times 2 is -6 plus 2 is -2, and then -5 plus this is 0, and 10. I have -5 times 2 is -10, -10 plus 6 is -4. And then I can do, well, I can make it clear by just saying, let's multiply -1/2 by row 2 and -1/4 by row 3. And that gives me the matrix 1, 2, 0, 1, 0, 1. And then minus row 2 plus row 3. This is 1, 2, 0, 1, 0, 0. So now because these are row operations, they have taken the span of this row space up here is still spanned by these vectors. Because that's a theorem that doing Gauss's method doesn't change the span of row space. So the span of these 3 rows is the same as the span of these 2 rows. And in echelon form, the row vectors are linearly independent. So in echelon form, the row vectors are linearly independent. And you can sort of see that, because what's going to happen is, like if I tried to look at these vectors here, I'd have A times 1, 2 plus B times 0, 1 equals 0, 0. Well, the first equation is A times 1 plus B times 0 equals 0. And the second equation here, here, and here would be 2A plus B times 1 equals 0. Well, the first equation here is going to give you A equals 0, and the second one is going to give you B equals 0. So that means these are linearly independent. And you can so the point is that once you get to echelon, if I have some vectors and I wanted to see whether or not they were linearly independent, I can apply Gauss's method to it, and I get a linearly independent set. So that means that's a way to find a basis mechanically without having to look and just grab a dependent vector and remove it, right? So I can use Gauss's method to find it, because that's what Gauss's method does. It takes a set of row vectors and makes them linearly independent. Now up here, I sort of jumped the gun because I said, well, this is the transpose matrix, right? Or I can see in here. So it's also made these. So the row space of these two, well, they are linearly independent. But I'm going to, because these, there's no free variable, but here is a more explicitly, I'm guaranteed that these are linearly independent. Okay, so there was a little bit of a hiccup there with I jumped the gun with this sort of punchline, but here's the idea. Let's say that you had these vectors, 1, 2, 3, and let me see, 3, 2, 1, and 4, 4, 4, right? And you wanted to find a base. You wanted to find a basis for the span of these vectors. Now, it turns out here that you can see it's not linearly independent, because this fourth one I just added 3 plus 1 is 4, 2 plus 2 is 4, 3 plus 1 is 4. So the fourth one's linear, but let's say I wanted to find that mechanically. I wanted to find a basis, right? Well, here's the idea. What you can do is I can take because Gauss's method works on row vectors. So what I do is I can form the matrix here of these ones here, which would be the coefficient matrix, of a linear system like C. But then what I can do is I don't want the linear independence of these rows. I want of the columns. So what I do is I take if this is M, I take the transpose of this matrix. Okay. My goal is to find a basis of these I want to find a basis of the span of S, the linear combinations of all these vectors. To do that, I will write these as row vectors. 1, 2, 3. First column becomes first row. Second column becomes second row. And third column becomes third row. Now, so what I'm going to do is then I'm going to then use Gauss's method to reduce this to echelon form, and that will give me a basis for row space here, and I can transpose back to the ones I want. I know this is a little bit involved, but so let's see what happens. I can let's subtract 3, 2. Let's do minus row 2 plus row 3. 1, 2, 3. 3, 2, 1. 3 minus 4 is 1. 2 minus 4 is 2 and is 3. Then that makes it clear that minus row 1 plus row 3 is going to give me 1, 2, 3, 3, 2, 1, and 0, 0, 0. So that's good. So then now this isn't quite an echelon form. So I want to do one more thing though, just to make sure that this isn't. I can see that this row is not a multiple of this to be sort of to go mechanically all the way. I want to do minus 3 row 1 plus row 2 and find 1, 2, 3, 0, 0, 0, and I'm going to get a 0 there. 2 times minus 3 is minus 6, plus 2 is minus 4, and is minus 9, plus 1 is minus 8, right? Minus 9 plus 1 is minus 8. And then to clear it up, I could do minus 1/4 row 2 and have 1, 2, 3, 0, 1, 2, 0, 0, 0. And then so then I know that 1, 2, 3 and 1, 2 are linearly independent, and these three vectors here, these two vectors here span the same space as these three. So if I go back and choose the set B equals 1, 2, 3, 0, 1, 2, the claim is that the span of B equals the span of S, which are these vectors up here, where S is the set 1, 2, 3, 3, 2, 1, 4, 4, 4, and this B is right here. So the claim is these span the same space. Well, now you could check that, but you have to sort of, this relies on some sort of, seems like sleight of hand or maneuvering, but it gives you a mechanical way to use Gauss's method to solve the problem of finding a basis from a set of dependent vectors, right? So we've used Gauss's method to take a set of dependent vectors and find a basis that's guaranteed to be linearly independent. And since Gauss's method never changes the span of row space here, it's not going to change the span of these vectors here. And there's going to be some kind of connection between, you can see here there's sort of this going back and forth between a matrix and its transpose where interchange rows and columns. There's some kind of connection here. And that's why transposes are relevant. I know this has been a lot sort of maneuvering to get this sort of connection here, but let's go back and look. This is the motivation here in this section on vectors and linear systems to say this is the definition. The row space of a matrix is the span of the set of its rows. The row rank is the dimension of this space, the number of linearly independent rows. So what we say is this matrix here, 1, 2, 3, 3, 2, 1, 2, 4, 4. If I go, see it has here 2 linearly independent rows. So what I say is the dimension of row space here equals 2, not 3, because it's spanned by these 2 vectors. So I have this 3 by 3 matrix, and it has a row space. Well, that row space, there is a basis, and the number of vectors in the basis is the dimension. So here the dimension's 2. So here's the definition: the rank of a matrix. Okay, it's a definition of this word rank. Rank of a matrix equals the dimension of row space. Well, so we have row space. The dimension is just the number of vectors in a basis, right? So you can see that the rank of the matrix is just the number of vectors equals number of rows in echelon form of matrix. Okay, so if I give you a matrix like this, 1, 2, 3, 4, 5, 6, 7, 8, 9, then and I ask you what's its rank, well, that would mean finding the dimension of row space. And to find dimension of row space, you use Gauss's method. To find a basis. And the rank is number of vectors in this basis.